Now we begin Chapter 4 with a discussion of probability distributions. So in this section, we're going to start by talking about what's called random variables. A random variable x represents a value associated with each outcome of a probability experiment. So really one of the new things we're introducing is beyond just the probability of something happening, we're going to have an associated value that goes along with that outcome. So we'll have both in this case now to do in our work in our calculations. So one thing we can also say is this implies that x is determined by random chance. The random variable x can also be called discrete or continuous. So going way back to one of the earlier sections, there was a discussion on discrete versus continuous. In this section, we're going to deal with discrete, but later we'll also talk about continuous as well. And just to recall, a random variable is discrete when it has a finite or countable number of possible outcomes that can be listed, such as whole numbers. Each number is separate, there's no number in between, so it's called discrete. A random variable is continuous if it has an uncountable number of possible outcomes, such as an interval on a number line. X can be any value between 0 and 24, for instance. That's a continuous, unbroken line between the two numbers. So when we talk about discrete, for a discrete probability distribution, it lists out each possible value that the random variable can assume together with its probability. A discrete probability distribution must satisfy these conditions. First, the probability of each value of the discrete variable is between 0 and 1 inclusive. This goes back to our discussion that a probability is any number between 0 and 1, including 0 and 1. Also, the sum of all the probabilities must also be equal to 1. This also goes back to our fundamental ideas of probability, where 100% chance that something in the set of possible outcomes will occur. So all possible outcomes, all the probabilities need to add up to 100% or 1 for that to make sense. So those are the criteria we'll have in our random variable, our probability distribution. Let's look at a table to give us an idea of what a discrete probability distribution looks like. Here we have the values of our random variable, which are 0, 1, 2, 5, and 6. And then associated with each of those is a probability of x, p of x, to go with it. Does this setup here meet the criteria for a discrete probability distribution? For that to happen, first off, every probability value needs to be between 0 and 1, including the numbers 0 and 1. And this is true. Looking at all the probability values, not the x values, but just the probability values, they all represent 0.25, 0.19. They're all numbers between 0 and 1. So that first criteria is passed. Second criteria was the sum of all the probability values must equal to 1. So if we add up the numbers, 0.25 plus 0.19 plus 0.09 plus 0.24 plus 0.23, they all add up to equal to 1. So since the sum is equal to 1 in the probabilities, this is a discrete probability distribution. Let's take out some numbers here and discuss what would need to go there to make it a legitimate probability distribution. So you've got your values of x, but we're not so much worried about those. The values of x can be anything. The probability values do need to fit the criteria of the two that were set out earlier. First off, we need to choose probability values which are between 0 and 1. We can have in this case, we're just choosing numbers that fit that description, so we could choose a lot of different things. And we also need the probability values to add up with those that are already there to get a sum equal to 1. We can choose from a variety of values. So for instance, here's two numbers that would work, 0.14 and 0.25. They're both between 0 and 1, and if we add them alongside the other numbers, we get a sum of 1. Here's another two set of numbers that would work, another pair of numbers. Again, they have to just fit those two criteria to make it work. They're between 0 and 1, And if we add them together with the other probability values, they all still add up to 1. So you can choose different numbers unless there's some other criteria for the probability distribution in a particular instance. As long as they fit these two criteria, then they are a legitimate probability distribution. Let's look at this frequency distribution. It has scores and frequencies to go with it. The description is: an industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a whole number score from 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. A score of 3 indicates neither trait. The results are shown in the table. We're going to construct a probability distribution for the random variable x. Okay, well, we've already got our frequencies laid out. Those are going to reveal to us the probabilities that need to go into the probability distribution. Starting out, we need to know the total frequency, which it already told us that, but if it didn't tell us that, we would take all the frequencies and add them together to get the sum of 150 in this case. Then we need to go through and list out the probabilities for each score. Recall, when we have frequencies and probabilities, we take the frequency divided by the total frequency. So for the first score of 1, the probability of 1 is equal to 24 divided by 150, which is a decimal of 0.16. Probability of 2 is 33 divided by 150, equal to 0.22. Probability of 3 is 42 over 150. Probability of 4 is 30 over 150. And the probability of 5 is 21 over 150. I'm going to take these individual decimal representations for the probabilities of each and put them in a table along with the scores. It looks something like this: the value of x and the associated probability. And we call this the discrete probability distribution. So having seen how we create the discrete probability distribution based off of the probabilities that go along with each value of x, we'd like to discuss what is the mean, or like an average, for a discrete random variable. That's given by mu is equal to sigma x p of x. What this basically means is we take each value of x for the random variable multiplied by its corresponding probability, and then these products are added together. The symbol sigma stands for summation. So the summation of all the x's and probability of x's multiplied together. Let's look at an example of that here, where we have our probability distribution, again, the one we created. And to create the mean of this random variable, we start by taking each value of x times the associated probability. So 1 times 0.16, 2 times 0.22, 3 times 0.28, 4 times 0.20, and 5 times 0.14. Those numbers that we get after multiplication are then added together to take the sum. So adding them together gives us 0.294. And this is what we call the mean of the random variable x. Mu equal to 0.294. Just like we talked about before when we talked about mean, we also followed up with a discussion about variance and standard deviation. Those also apply to a discrete random variable as well. The variance of a discrete random variable is sigma squared, equal to the summation x minus mu all squared times p of x. And the standard deviation is the square root of variance, so just the square root of that calculation. Let's go to our table of values and do the variance and standard deviation. So to do that, we're going to start by doing the steps here, which kind of mirrors the steps we did before for standard deviation. We subtract the mean from each value x, then we square each of those differences we get from subtraction. Then we multiply, and this is the new thing, we multiply by the probability values. Then we take the sum of all those values together. So like the first two steps would be identical to what we did in standard deviation. Subtract the mean from each number, square it after doing subtraction. But the next step that we did was to take the sum. In this case, we'd have to multiply by the probabilities, then we'll take the sum of all those numbers together. Here's what that looks like in this case. So we've got our values of x and the associated probabilities. The first thing we're going to do is take each value of x and subtract the mean away from it. So we found the mean to be 0.294. So I went through and I subtracted each value of x minus 0.294. Then we need to square those numbers. So the first one we have to take negative 1.94 raised to the second power, the negative 0.94 raised to the second power. And here's all the numbers I got from doing that. So after we did the subtractions, now becomes kind of the new thing that we're doing in this particular instance. We're going to take each of these numbers after squaring and multiply it by the respective probability values. So we have to do the 3.7636 times the probability 0.16, the 0.8836 times the probability 0.22, and so on through the rest of the numbers. So we're going to have some long decimal numbers. I'm keeping them in fairly long here so I don't round too much. But once we did this step, comes the last step where we sum all these numbers together. So if we add together all the decimal numbers we got after multiplying the probability, the sum is approximately 1.6164. That's what we call the variance, and I went ahead and rounded it to 1.62. The standard deviation would just be the square root of 1.62, which is 1.3. This leads us into also a conversation about what's called the expected value. The expected value of a discrete random variable is equal to the mean of the random variable. In other words, we use this e of x as denoting the expected value. It's equal to mu, the summation of x times p of x. And so as we've seen calculated, this process involves taking each of the values times the respective probabilities and taking the sum of all these products. And in words, I like to say it could be thought of as the value 1 times the probability 1 plus the value 2 times the probability 2 plus and so on through the rest of the values and probabilities. Let's look at a table, and I'll do this one by hand to show you the calculation of the expected value. Okay, so let's get started here, and to do the expected value, we'll take our table of values. Each value is the letter x, and we multiply that times the probability. And this came from a slightly different textbook, so they write things slightly different, but the idea is the same. The probability values and the values of x. So to do the expected value here, what we're going to do is take each value, so starting with negative 2, times the respective probability of 0.05. We're taking the summation here, so we have to add these together with the next thing, where we take the value negative 1 times its probability 0.30 plus 0 times 0.25 plus 1 times 0.40. And so we could just do that calculation however you'd like to. I'll throw it in the calculator and see what we get. In this case, it actually really just sort of cancels itself out and gives us an expected value of 0. The next calculation we're going to do is the variance. Now I went ahead and made a note that in some cases, some textbooks likes to abbreviate it as VAR for variance. So it's the same thing. But we're using sigma squared in a lot of cases to denote variance. So to do that, we need to do the summation x minus mu raised to second power times p of x. So in order to do this, we need to know the mean, mu, which is also equal to the expected value, which we found it to be equal to be 0 in the last step. So they're equivalent to each other. So if we go through and we subtract the mean, well, it doesn't really do a whole lot. It's just like -2 minus 0. So it's just -2, -1, 0, and 1. And if we go through and then if we square these numbers, we'll get 4, +1, 0, and 1. And then we take each of these numbers and we multiply it by the respective probability values. So we'll get numbers like 0.20, 0.30, 0, and 0.40. And then the formula, we need to take the sum of all these numbers here, which gives us an outcome of 0.90 for the sum. So we call that the variance, sigma squared, is equal to 0.90. Here's another example where we'll do expected value. The game being played here is with a dice. So the standard 6-sided dice, numbers 1 to 6. And the game works this way. $1 is 1 for a 1. $2 is 1 for a 2, $3 for a 3, $4 for a 4. However, losing happens when a 5 or a 6 is rolled, and the loss is $6.50. So in this case, we have our values, which are the money winnings, and the probabilities we can also calculate to go with those values. Let's look at that. So first off, we're going to find the expected value, where we need to take the value times the probability plus the value times the probability, and we add them all up together. So starting out with probabilities, let's write those down. For a 6-sided dice, the probability of a 1 is just 1 out of 6. The probability of rolling a 2 is also 1 out of 6. The same for rolling a 3 and rolling a 4. However, probability of rolling a 5 or a 6 can be calculated by taking the probability of 5 plus the probability of a 6. So 1/6 plus 1/6 gives us 2/6 or 1/3 probability of rolling a 5 or a 6. That allows us then, we'll write down the values to go along with it: $1, $2, $3, $4. The value of losing money, however, is expressed as a negative value. So losing $6.50 is written as -$6.50. So with our values and probabilities together, we can create the table for the discrete probability distribution. Looks something like this. The dice rolls and the respective values to go with it and probabilities. And so we'll go through, we'll multiply values times probabilities and add them up. So $1 times 1/6, $2 times 1/6, plus $3 times 1/6, plus $4 times 1/6, plus -$6.50 times 1/3. This comes out to be equal to -50 cents, -0.50. And we can interpret this as the expected value. And in terms of expected value, we could also understand this, that if this game is played several times, then this is also referring to the average winning or losing in the game. In this case, since it's a negative number, it means that on average, there's a loss of 50 cents per game if it's played over the span of several games.